Okay, well, let's review where we were last time. We've been doing modeling this semester so far, and based on our modeling, we can then, once we learn how to write unstable models, because unlike your other classes, we're in the real world here in unsteady state land, we're going to be able to, once we know how to write and analyze unsteady models, then we're going to add control to our models. But first we have to learn to walk before we learn to run. So if you remember, we started out by writing models that were linear and solving them. And all the models we were coming up with were first order linear differential equations that we saw had solutions if A and B were constant like this, and if A and or B were not constant, then we had to do various integrals. Not a big deal. But that was, of course, simplified real-world land, where everything was linear. Unfortunately, in the real world, things are not usually linear. On rare occasions, they are. When they're not linear, we can very rarely actually solve the equations exactly. Sometimes we get lucky analytically. So we can either solve them numerically, which today is not that a difficult problem, or we can linearize the equations. That is, we can approximate curves by straight lines. We can approximate surfaces by tangent planes. And as long as we don't go too far from the point at which we're taking the tangent, those are pretty good approximations. Obviously, if we go far away, they're not very good. And to do that, we have to appeal to Taylor's theorem, which tells us how to write the value of a function in many locations in terms of the value of a function at a single location. So if I know the value of the function and its derivatives at one point, then we can write the value of the function exactly at all the other points by this approximation. And we can truncate wherever we want. So if we're interested in linear approximations, we truncate after the linear term. And then we have an error term, which can give us an estimate of the size of the error when we use the maximum value of the next derivative in this neighborhood. We did originally an example where we had only one independent variable, one thing that was varying the size of the dependent variable. And that was the case of the reactor with the second order reaction. Then we decided to look, of course you can do this when you have many independent variables. And here we wrote down the form when we have two independent variables, x and y, or two things that are varying in a nonlinear manner. So, and to look at that, we looked at a CSTR heater where we have fluid coming in with a density, specific heat, a volumetric flow rate under everything. So there's a certain inlet temperature of the cooling fluid, a density, a specific heat, and a volumetric flow rate. And this cooling, the fluid coming through the cooling coil would cool the fluid in the reactor and therefore change the temperature. So the reason why the temperature would change here is if we change VC. So if VC goes up, then there's more cooling fluid going through here, and therefore the temperature coming out should be lower. So that's the basic idea. We want to calculate the time dependence of the temperature of the fluid in and coming out of the reactor as a result of this change for t greater than 0. We want to know what happens over here. So we started analyzing that, and we noted, or we were given, that even the overall heat transfer coefficient of the coil is a function of VC. So it's not just the amount of heat transferred out due to the flow of the coolant, but even the efficiency of that transfer is a function of VC. And we said, all sorts of stuff got erased here. How dare they erase what we're doing? But what we had here was, what we were left with was this was given, where we had the overall heat transfer coefficient times the area of the coil, this is U of the coil, UA, was equal to alpha VC to the beta. This is not a fundamental equation. This is a correlation that people did from experiments. So there's no fundamental reason why that's the case. Although you could imagine that if the velocity is higher, well, why would this be the case, be this positive? Then the flow in the coil becomes more turbulent. So you have better mixing between the center of the tube in the coil and the fluid near the edges. If the flow is laminar, then the hot fluid is going to be near the boundary of near the wall of the tube, and the inside will still remain cool and only be a heat transfer due to conduction radially inward. But if I increase VC, then I don't have laminar flow anymore, and the cold fluid from the center of the coil gets transferred to the wall, so I increase the heat transfer coefficient. So that's physically why this makes sense. That is, the higher VC, the higher the overall heat transfer coefficient. That's the physical reason, but the actual functional form comes from just doing the correlation. Okay, and what we did is we wrote down a steady state balance for the coil, because we said the coil is much thinner and the flow, VC, is typically much larger than V. So the time scale in the coil is much faster than the time scale in the reactor. The time scale in the reactor is roughly tau. So the volume of the volumetric flow rate, whereas here, the volume of the coil is small and the volumetric flow rate is large. So the characteristic time in the coil should be presumed much faster than the characteristic time in the mixing tank. And therefore, we can do a steady state balance, or try a steady state balance, on the coil and an unsteady balance on the reactor. So those were two equations. The third one was UA as a function of VC, and then we needed another equation that related the Q, the amount of heat transferred, to UA. So it was UA delta T. And so what we did is we combined, we don't know TC out a priori, so we combined these equations to eliminate TC out. So there's no TC out here. And we also eliminated one of the other variables, which I don't remember which one it was. TC out we eliminated, and something else. We got to it last time. And so what we're left with is T is the unknown, T in is known, tau is known, TC in is known. All these things are constants. All these things are constants. UA is now a function of VC. So we start out with 4 equations, and once we plug this in for UA, we're only left with one equation, which is what we want. So that's a review of how we got where we are today. Any questions on that? Or any do is do a little erasing. This is from a previous problem, I think. Oh, I didn't want to erase that. In a single equation, we would put this alpha VC to the beta for here and here. And I'm going to rewrite it in a second. And so let's rewrite it now. So I have dt is equal to T in minus T over tau plus TC in minus T over rho Cp hat V times alpha Vc to the beta divided by 1 plus alpha Vc to the beta over 2 rho C CPC Vc. Now, I don't want Vc in the denominator of the denominator, so I'm going to multiply top and bottom by Vc. So all I did is I plug this in, and I'm going to multiply top and bottom by Vc. And if I do that, this disappears, this turns into a Vc, and here I get a beta plus 1. So I just multiply top and bottom by Vc. And I want you to notice, this is linear. There's only one thing changing here, T. Only one thing changing here. But there's too many things changing here. There's Vc changing here, here, and here. And there's T changing here. So this term is very nonlinear, as I said here. So I have to take this term, and which is a function of T, capital T, and Vc, and take the derivative with respect to temperature time, take its value for t less than 0, take its derivative with respect to temperature times t minus the initial value, plus the derivative with respect to Vc evaluated at t less than 0 times Vc minus Vc at t less than 0. It's exactly this equation here. The value at xy is the value at x0 to y0. That's the initial, the t less than 0 value, the initial value, which is the value about which I'm doing my linearization. Plus the partial with respect to the first thing that's changing, evaluated at x0, y0. That's this thing, t is the first thing changing, evaluated at the initial condition. The initial value which I'm linearizing, times x minus x0, plus the derivative with respect to the second thing that's changing, Vc, evaluated at the point about which I'm doing linearization, which is the initial condition, and Vc minus Vc t less than 0. It's exactly what I have here. So let's go through and do that. So I notice that this term, which I need a letter to call it, let's call it, I don't know, E is equal to, it's equal to, as we said, it's E for t less than 0, plus dE dt at t less than 0, t minus t0, plus E dVc for t less than 0, times Vc minus Vc t less than 0. And this should be t at t less than 0. I just rewrote this equation here. Maybe it's slightly clearer because I'm writing out the word term. So let's calculate these things. Notice that this whole thing, if when I take dE dt, what do I get? This thing, remember, is just UA. That thing was just UA. Yes. So dE dt is just UA for t less than 0. Because this stays the same. When I take the derivative, I just get a minus 1 here, divided by rho Cp hat V. And so is that clear? When I take d dt of this, I just get a minus 1 here, and everything else comes along for the ride. And dE dVc, well, that's equal to Tc in minus T rho Cp V times the derivative of this with respect to Vc. So it's a mess, but I'll just do the algebra quickly. It's just take the product rule. So it's f prime g beta plus 1 alpha Vc to the beta times g Vc plus alpha Vc beta 2 rho C Cpc at minus fg prime, so minus alpha Vc beta plus 1 times the derivative, 1 plus alpha beta Vc to the beta minus 1 over 2 rho C Cpc at over g squared over Vc plus alpha Vc to beta over 2 rho C Cpc squared. I'm never going to write that again, at least not this semester. But everything in here, notice you have the variable t and Vc. So I'm going to call this thing B. Let's call this B. And I want to evaluate it. And I'm going to evaluate it for t less than 0. So this is B for t is equal to t for t less than 0. And Vc is Vc for t less than 0. And I'm going to call this thing B0, or B less than 0. So now I can plug in to here, and for the unsteady, I have dt is equal to t in minus t over tau plus, and let's see what I'm left with. Well, I'm left with this thing, which is its value e at t less than 0 plus or minus ua over rho cp hat v. This is at t less than 0 times t minus t of t less than 0 plus this mass, which I'm going to call b at t less than 0, because I don't want to rewrite it, times vc minus vc at t less than 0. And of course I have a remainder term that I'm going to drop. Now what's the great thing about this? The great thing about this is this term was highly nonlinear. I have VC's to powers all over the place, and it's multiplied by t. However, this term is purely linear. I've got 1t here, 1t here, 1t here. This is a constant. 1 VC here. This is a constant. So I take a situation or a term where everything's jumbled together. VC's changing. The numerator's changing. The denominator's changing. T is changing. Everything's jumbled together, and I break it up into just the sum of just the temperature part and just the VC part. Is that exactly correct? Well, it's as correct as this plane is correctly modeling this surface. As long as I'm close to this point, I'm okay. If I get far away, I'm not okay. What does far mean? Well, I have to look at the remainder to know what close and far is. Questions?
So what do you compare the remainder to?
Well, we'll look at the remainder, we'll talk about the remainder after we solve the problem. But what you have to compare the remainder to the actual terms. So for example, you compare the remainder term to the size of the last term. So if we truncate here, you compare the remainder to the size of these terms.
So the last terms.
Yes.
Also, may I request that you write a little bit larger? It's easy to get lost in the subscripts and exponents.
Sure, just keep reminding me if I'm a recidivist.
Still want to
Do you know the word recidivist?
No.
It's when criminals get sent to jail for like robbery and then they come out and they start robbing again. So even though I'm intending to write bigger, sometimes I'm a recidivist.
Can I interject?
Please do.
Okay.
Please do. As I mentioned many times, interject as much as you want. It just shows me you're interested, which is a good thing. It's when you're quiet that I don't know if you're interested. Okay, so now let's take this, remember, let's take the steady state version. The steady state version, I have 0, and this is dt for t less than 0, because I'm assuming that at t less than 0, t was at steady state. That's a given. And that's equal to t in minus t for t less than 0 over tau. And this term, I can keep the whole thing, because at t less than 0, so notice this term should normally have all three of these terms. But for t less than 0, t is equal to t less than 0. So this one would be 0. And vc was vc for t less than 0. So this is 0. So I just left with this. And now we can subtract. And if we subtract, I can erase some of this. And let's subtract. I don't have room to subtract down here, so I'll have to subtract up here. Unless I wrote too small, and then I would get yelled at. So ddt of t minus t less than 0, t minus t less than 0 is t prime. So that's ddt of t prime. T in minus t in, well, t in hasn't changed. The only thing that's changed is vc. So these terms cancel. So now I just have minus t of less than 0. That's t prime. Minus t prime over tau. Well, I'll bring to the other side of the equation plus t prime over tau. It should come in with a minus on this side. I just bring it to the other side of the equation. E cancels. These are the same. So this cancels this, and this cancels that. All right, so what am I left with? Here I have minus UA less than 0 over rho CP hat V times t minus t less than 0 is t prime. Well, it came in with the minus on this side of the equation, so I'm just going to move it to the other side of the equation. And that's equal to B, t less than 0, times BC prime. Look how simple that equation looks. Much easier. And notice, it's exactly of the form we're used to. Plus 1 over tau plus UA over rho CP hat V times t prime is equal to beta t less than 0 BC prime. And I'm sorry I made these t's temperatures. I was trying to use script t's for temperatures. So my error, but I'm not going to go back and change them. So I'll use T1 for a time constant. So notice this is exactly the right form. This is A, and this is what we call B. And my time constant, T1, time constant, is equal to 1 over tau plus UA over rho CP hat V. And this is UA at t less than 0. By the way, you don't have to worry if you copy every last thing I write on the Blackboard, because I'm posting pictures of Blackboard notes and the video. So it's more important that you understand. If you miss a subscript, you'll get it later. By the way, it is a good thing to take notes. There have been many studies that when you take notes, as opposed to just listening, it sinks in better, you retain it better. That's sort of in the educational literature, which I don't usually read, but I did read a paper about that. But you don't have to take copious notes with every detail. But the act of actually synthesizing what you're hearing into some notes actually helps to implant it in your brain. I'm sure we could write an equation for that if you like. That would be fun. I'm kidding. Okay, so let's notice that as the heat transfer coefficient goes up, the time constant goes down. That makes sense. If the heat transfer coefficient goes up, so remember we had we're looking at T out. As the heat transfer coefficient goes up, well, the temperature should change faster in here. So the time constant should go down. On the other hand, for the same heat transfer coefficient, the bigger the volume of the tank, the slower the time constant. So it's going to take longer for the temperature to change. Similarly, as tau is the volume over the volumetric flow rate. So the volume is in the denominator here. It has the denominator of 1 over tau. So it also has the same effect. The bigger tank, slower the time constant. The higher V, the higher the flow rate of the tank fluid, well, then the higher that, the slower, the faster the time constant. If you keep exchanging the fluid, then the temperature is going to change faster. So all that stuff makes sense. Let's write out the solution. Well, again, we appeal to this overused equation. And remember that because we're using prime variables, all the initial conditions are 0, because the prime is the function minus the initial condition. So if the prime is always 0 at the initial condition, because the initial condition minus the initial condition. So all I need is the second term here. So I have t prime of t, and this this is for t greater than 0, is equal to b over a. So that's this b for t less than 0, divided by a, which is 1 over tau, plus ua at t less than 0, rho cp hat v, times 1 minus e to the minus at, where this again is a. I don't feel like writing it over again. So I just have a 1 minus an exponential, and it looks like this. And as t goes to infinity, what can't you see? E to the minus at, where this is middle a. So instead of straining your eyes, I don't want you to need glasses by the end of the course. Just ask me. What's that? If you're doing that, I can't help you. Sorry. There are a lot of things I can do, but curing myopia is different. Although there was a store, I like the, sometimes when there's a business that has a clever name, I really like it. So there was one place on East, they closed right around the pandemic. There was a glasses store on East 8th Street and First Avenue that was called My Optics. I thought that was a really clever name. Anyone like clever names of businesses? Okay, here's one that's even better. There was a company I saw that took down buildings. You know, before when you're going to build a new building, they call in a company to take up the old building. And they called the company Edifice Rex, which I thought was a wonderful title. Edifice Rex. Okay, let's get back to this. So this goes to a limit as t goes to infinity. What's that limit? Well, as t goes to infinity, the exponential, it's e to the minus at goes to 0. So this thing is the value of t prime as t goes to infinity. This is the value that it goes to. And did I lose something? I lost something. Notice, yes, I need a VC prime here. There's a VC prime. So in here, there's a VC prime. Because b, little b, is big B times VC prime. Let's see what VC prime is. VC prime is VC at t greater than 0 minus VC at t less than 0. So since it's a step change, it's just delta VC. So I'm going to rewrite this equation because it's a little cramped here. And I still want to leave Taylor up here, but I don't necessarily, I'm going to leave Taylor up. What can I get rid of? I can get rid of this. This is from last time. So let's rewrite that equation. I've got t prime of t, right, nice and big, is equal to b plus over 1 over tau plus ua rho cp. Delta VC times 1 minus e to the minus 8. So there's the solution. And what we noted was this product here is the limit, it's t prime of as t goes to infinity. Because as t goes to infinity, the exponential is 0, I'm just multiplying by 1. And we know earlier in the semester, we spoke about steady state gain, which we could do Kp for Vc, steady state gain. And that's the value of the output over the input change as t goes to infinity. So it's the value, it's the ratio of the change in the output to the change in the input. Well, the change in the input, in this case, is just delta Vc. And the change in the output is just this thing. It's t prime. So if I take this thing and I divide by delta VC, I just get P for t less than 0 divided by 1 over tau plus UA t less than 0 over rho Cp hat V. So we now have the steady state gain, which is the ratio of the change in the output to the change in the input. And why is that useful? If I want, often we would, because in your other classes you were brainwashed, it's not a nice way of putting it, to always love steady state. Chemical engineers love steady state. It's their first love. But sometimes, as happens, you get jilted by your first love, and you're in unsteady land. But when you're in steady state land, you want to know if I want to accomplish a certain difference in temperature at steady state. I want to accomplish a certain drop in the temperature at steady state, knowing the steady state gain. So this is sort of ignoring the dynamics. I want to ask, how big should my change in the input be if I want to, at steady state, get a certain change in the output? Well, so if I'm ignoring the dynamics, all I have to do is say, if I want a certain change in the output, just take KPC and multiply it by the change in the input. Or the other way around, if I want to know what the change in the input would be, I take KPC, well, I take the output that I want and change and divide by KPC. So if I just put it here, the desired delta output is equal to, the desired output divided by KPVC is equal to the change I need in the input to get it. The change I need in the input, do I have that upside down? The change in the input I need to get a desired output is the change in the output over KPC. Change in the output over KPC. So that's what's useful for KPC. So if we're only interested in the steady state, that's it. Otherwise, we get the dynamics here. Are there any questions on that? Yes, please. What does the P subscript mean? Good question. I don't know what the P subscript. It's just the convention is to write it as KP. I'm sure there's a reason, it's just not coming to my head right now. But whenever we use it, we'll call it steady state gain. And we need some sort of subscript because just a K is not specific enough. There are Ks for everything. But yeah, I'm not sure.
Yeah, I guess I'm just confused because earlier we treated VC as a variable.
It is a variable, yes.
Okay.
But remember, it's a variable that undergoes a step change. So for t less than 0, it's one value, VC t less than 0. And then for t greater than or equal to 0, it jumps to a new constant. And it stays there. So for this particular change in VC, a step change, I can characterize it by just one number, the difference between the new value and the old value. In general, if I have other types of changes, I get other types of, then it really is a thing that's constantly changing. Here it ends up just being a number, VC prime. But you still sound like you're not happy.
Well, it's just because earlier we had to take this partial differential to get
Yes.
the solution. But then later we just characterize it as delta VC.
We took the partial derivative. We did take the partial derivative because, remember, the temperature, which is what we're interested in, depends on the value of VC, the temperature and VC. So the temperature has changed at t equals 0. So I need to know how VC has changed at t is equal to 0. So part of it, if I look at the expression E, VC has all of a sudden jumped. It used to be one value, now it's a new value. It's changed to a new constant, but it's different from what it used to be. The system used to be at steady state, at a different value of VC, at this value of VC. So we want to know not how VC changes. We know how VC changes, that's a given. We want to know how that affects how T changes. How T changes. So that's why we're taking dE dVC, because E comes into the T equation. We want to know how T changes because we changed VC. So that's why we need it. We're not interested in an unknown VC, how VC is changing. That's known. But because we changed VC, we changed the heat transfer coefficient. So, and that changes the temperature. So we want to know how that change in VC has changed the heat transfer coefficient, which changes the temperature.
That's clear.
Other questions? The more questions you ask here, the less you have to figure out on your own. Okay, let's see if there's anything else I want to say about this. Yeah, so how do we know, let's go back to the question that someone in the front asked, is how do we know, I keep on ignoring the remainder because it's inconvenient. How do I, and I keep saying, as long as you're close to the point where you take the tangent, you're okay. Well, what does close mean? Well, to draw a little picture, not that I have a lot of space here, but I'll eventually erase the blackboard. It gets a little messy when I try to keep the writing from last time instead of starting from scratch. If I have this curve and I replace it by a tangent at this point, well, clearly this is good and this is bad. On the other hand, it depends on the curve. If the curve looks more like this, then what's close and what's far away is different for the pink curve and the blue curve. The blue curve, this is far away over here. The pink curve, it's not really far away over here. You see the difference? Why is that? Well, this tells me that the derivative of the blue curve is somehow changing faster than the derivative of the pink curve. Derivative of the blue curve, if the derivative is changing faster, that means it has a bigger second derivative, right? The first derivative is changing faster, the second derivative is bigger for the blue curve than for the pink curve. That's exactly what the error term says. The error term says if you chop off at the first derivative, you look at the second derivative. If the second derivative is really big, then you can't go as far away from the point about which you're taking the linearization, because the product has to stay smaller than the term you're keeping. So the bigger the next derivative, the closer you have to stay to the point of interest, to the point about which you linearize. So here again, the pink curve has a smaller derivative, so I can go further away for it to still be considered close. The blue curve has a bigger second derivative. The first derivative is changing faster, so I can't go as far away. So, that's the physics, the physical picture of what the remainder is telling me. How do I know if I'm doing well? Well, one easy way to see if I'm doing a good job is if I look at the steady state gain. Actually, or just look at T prime as T goes to infinity. Look at this thing. I look at T prime as T goes to infinity. If I've stayed close enough, then the experimental value should be very close to this value. If I've gone too far, it's not going to be very good. So that's one way of telling. Another way of telling is to actually calculate if E is an analytic function. So what I could do is actually take the second derivative, I know how big the first derivative is, because it's analytic. I know how big the first derivative is, and then I can just take the second derivative and see how big the biggest value that it has in a certain neighborhood. and that'll tell me how big the neighborhood can be. If I want to keep it less than the first derivative, I have a value for the first derivative, and I know the second derivative as a function of position, and I could look to see how big a region can I get away with to keep this term much less than this term. So those are ways of dealing with that. Any questions on that? All right, so I'm going to end this problem, and that requires me to erase the blackboard. So you take pictures of just these two boards. And it's not obvious why, because it's not clear if this mess with the t and all the VCs, if separating, linearizing it is going to give you an overestimate or an underestimate of that term. It turns out it gives you, the linearization gives you an overestimate. It shrinks a little too much. Okay, let me erase. That picture wasn't as bad as I thought. I got the idea wrong. Okay, so what happens if we want the exact solution? We found that the Kp, that the t prime as t goes to infinity for the linear problem just isn't good enough. It ain't doing the job. That the real value is just a lot different. So if we have to solve it exactly, then we need to do numerical solution. Of the differential equation. In this case, these are ODEs, ordinary differential equations. Now, there's a whole course in this called numerical analysis, which is currently, it's an elective, which I end up teaching once in a blue moon when there's enough demand for it. The plan is to make that one required at some point, because it's a bit pathetic that we have in 2020 something, we have, it's not required in the curriculum for engineering graduates to know how to program a computer. So, that's part of the curriculum that some of us are pushing to change, and that the alumni students who've gone out working have said, you got to change this. So we all agreed, and even the external review board agreed. So it will be required at some point. But how do you solve an ordinary differential equation? So an ordinary differential equation is, say, df, let's say dy dt is equal to f of y in t. It could be an explicit function of time. With an initial condition, it's a first derivative, so then I have initial condition, y at t equals 0 is y0. So this is the problem. And how do you solve it? Well, the simplest method is Euler's method. And in Euler's method, we write y of t, let's say y of tj, is equal to y of tj minus 1, where obviously I'm labeling the times. On a computer, even though we think of an ordinary differential equation as continuous, computers are inherently discrete. So they're discrete values. So I can label the t's, t1, t2, t3, plus dy dt times tj plus 1 minus tj. Now this comes from Taylor's theorem. Taylor's theorem says, the function is the function of the last one plus the derivative times the difference plus higher order terms. If I evaluate the derivative at z0, then I have an error term, which is the second derivative. Is that clear, the relationship there? The question is, when I do a numerical calculation, where should I evaluate dy dt? Because there's a finite difference between tj minus 1 and tj, and I did j minus 1 and j, so this should be j minus 1. Well, so there are a few choices. Choice one. Choice one. One is I evaluated at tj minus 1. If I evaluated it at tj minus 1, then everything on the right is known. I know the value of tj minus 1 because that was here. So I know the function and its derivative at tj minus 1 because I know f is explicit. So if I know tj minus 1 and I know y of tj minus 1, I know f of tj minus 1. So I can just solve for this, and that's called an explicit Euler. The problem is, with explicit Euler, I've got an error term that is the second derivative at some value t star, somewhere in there, where t star is between tj minus 1 and tj, times 1 over 2 factorial, times tj minus tj minus 1 squared. So the error, if I decrease the time step, only goes down as the square. That's pretty slow, the square. It would be great if, when I halve the time step, if it went down by 2 to the 5th instead of by 2. The error goes down slowly. The nice thing is I can calculate everything straightforward. Let's go to choice 2. Choice 2 is where I evaluated at tj. So I want to evaluate this at tj, but I don't know its value at tj, because dy dt at tj, I need to know y at tj, and that's what I'm trying to calculate. So I have to solve it implicitly. So I choose a value and I cycle through. So this is called an implicit Euler. It has a similar error term, but it turns out it's much more stable. What does stable mean? Stable means when I try to solve things and I go further out in time, the solution could blow up if it's unstable. Not the real solution, the thing I've calculated. Then my errors add up so quickly that the solution is terrible. It turns out that implicit solutions are much more stable. The way the error adds up, it doesn't blow up nearly as easily. I need much bigger delta t's for the error to blow up for an implicit equation, a solution, than for an explicit solution. Now, this is not a course in numerical analysis. I just want to give you a sense of what you can do. How can I decrease the error? Instead of having it go as tj minus tj minus 1 squared, I can try to make it go at a higher power of tj minus 1. And one way of doing that is to evaluate, not at, so this is saying I'm evaluating either at the left endpoint or at the right endpoint. It would be better if I could evaluate at the middle. The middle is a better approximation, but I don't know the value of the middle. So I can try to add tj minus 1 plus tj over 2, but I don't know that exactly, so I can approximate that by the same equation. So I can approximate that by f of, well, by y of I want to evaluate it. So by y of tj minus 1 plus dy dt times tj, I think it's, no, I use j and j minus 1, by tj plus tj minus 1 over 2 minus tj minus 1. In other words, how do I get y here? So y at tj plus tj minus 1 over 2 is about equal to what it was at the left endpoint, plus now only go halfway across the interval. And this estimates y at the midpoint, and then you use this, plug this into f of yt to get at the midpoint. And that will allow you to evaluate this at the midpoint. So if I do this, if I try to evaluate dy dt at the midpoint of the interval by using an Euler step to get to the midpoint, then it turns out that my error, you have to prove this, will now go as delta t cubed instead of delta t squared. And I can repeat this. I can say, well, how do I know what dy dt is at this point? So I can again use another Euler way of doing the same thing. And this method is called Runge-Kutta. Or Runge-Kutta, I don't know the right way to pronounce that. Typically we use fourth order Runge-Kutta is common. And there the error goes as delta t to the fourth power. In other words, if I cut the step size in half, then the error goes down by the power of 2 to the fourth, which is 16. So if I cut the step size in half, the error is 1/16 of what it was before. And that's usually good enough. Are there any questions on that? Again, this is not a course in numerical analysis. This is a commercial for the course in numerical analysis. Now, one thing I should mention, I'm going particularly slowly today, I don't know why, is that when we solve equations, particularly in kinetics, if you're used to kinetics, you have many different, you typically may have many different reactions. If you have many reactions, sometimes the rate constants can vary by many orders of magnitude. And not only in kinetics, but kinetics is sort of the obvious case, where some reactions are just orders of magnitude faster than other reactions. So if you want to solve all those equations at the same time for the concentrations of all the species, you've got this problem that you have time constants, some that are very big and some that are very small, and maybe everything in between. And it turns out, if you try to use an explicit method, Euler or another explicit method, you get run into the following problem. If you want to decrease the error, well, you decrease delta t. If it's Euler, you decrease it by delta t squared. If it's Runge-Kutta, it's delta t to the fourth, if you make it explicit. The problem is your computer only can store a finite number of digits. So typically it stores 8, and if you've got a double precision, it does 16. It represents a number by 16 digits. You don't have 1,000 digits after the decimal place. So what happens is you're always rounding off. You're rounding off either at the 9th or at the 17th digit. You're neglecting or rounding. Well, if you have very, very different size time constants, then what happens is as you make delta h smaller, delta t smaller, yes, you make the method more accurate, but you lose accuracy because you're doing rounding errors if things are changing very little. So for example, your time constant is very slow. So one of the time constants is very slow, so not much changes. It's in the 17th significant figure, and you're dropping that. And what happens when you have that, the equations are called stiff. Stiff equations means as you decrease, you want to make the method more accurate by decreasing delta t, the method becomes more accurate, but the numbers become less accurate because of the round-off error. So you can't make delta t too small, because if delta t is too small, then the changes are happening in the round-off, not. So what do? So the stiff equations come up very often in many problems, particularly in kinetics. And it turns out that because implicit equations are more stable, they also handle this round-off error much better. So there's a particular method called Heer's method, which is a generalization of this implicit method of Euler, but it's a bit more clever. And it's an implicit method, so you have to solve it by iteration, not explicitly, but it can handle these problems much better. It's much more stable. Another way, if you just want a quick and dirty method, is you might just assume that all the fast time constants have already gone to infinity. That is, all the processes with the fast time constants are at infinite time. They're all at steady state, and then you only solve the reduced problem with the slow time constants. That just means you're interested only in what happens over the slow time, the long time scales, not the short time scales. Are there any questions? Okay, well that concludes the material for exam 1, and now we're ready for the material for exam 2. And what is the method for exam 2? Well, remember we've been solving these linear first-order differential equations that we either got naturally or by virtue of linearization by just integrating. Yes?
Do we have a date for exam 1?
We have a who?
A date for exam 1?
We have a date for, as I said, it's roughly either a week from today or 2 weeks from today. Because 2 weeks, but it's probably going to be 2 weeks from today. Because you still have to do homework. I have to give you homework for the rest of this. Okay, you know, again, it's always plus or minus 1 day depending on how fast we go. Okay, so we were solving, which we did just by the methods of ordinary differential equations, solving. And we saw that when we solved, once the equations got complicated, for example, not all that complicated, 2 CSTRs in series, I filled up all the blackboards with algebra just to get the answer. Imagine if I had 5 CSTRs in series. I'd be here all day and I'd need 20 blackboards. So the question is that, and that's a perfectly good way of doing it, but the more you write, the more likely you are to make mistakes. Even me. Same thing. So is there another way of doing it? And there's another method called the Laplace transform, which you may have had a taste of in your differential equations class. Now what's the idea of Laplace transforms, as we'll see? It allows us to solve constant coefficient ordinary differential equations. They don't have to be constant coefficient, but they work best with constant coefficient really easily. They don't have to be constant coefficient, but with a lot less writing than what the method we used before. It also turns out that they're going to be useful for input-output models. As we'll see a little bit later in the semester, we're going to make these diagrams with boxes, where a box corresponds, let's say, to a reactor or a heat exchanger. And we'll look at what comes in and what goes out, and Laplace transforms are perfect for models that look like that, with input-output. And we'll see that in detail. That's not going to mean anything to you now, but it will later. The other thing is, if we have, instead of just step changes, other kind of changes, where instead of, we had a steady state and then we go to a sine function with a certain frequency as the input. So in the last problem, instead of VC going from one value to another, VC starts to oscillate. So how do you solve that? If I know the frequency of the oscillation of VC, what's the frequency? Will T oscillate, and what's its frequency? Laplace transforms make that really easy. The other thing is, if there's a change, let's say in VC, how do I know that T is not going to blow up? So for example, if I have an exothermic reaction, a reaction that's very exothermic, and I have a heat exchanger, and something happens to the flow rate of the coolant in the heat exchanger, how do I know that the reactor isn't going to go up to high temperatures and melt? How do I know that the pressure, once the temperature goes up, isn't going to get high enough that the reactor is going to explode? And those sorts of analyses are very easy to do with Laplace transforms. So that's sort of the motivation. And so let me define for you what a Laplace transform is. So if f of t is single valued, and what else do I need here? F of t is single valued for t, and let's make it simple. F of t equals 0 for t less than 0. Then L of f, the Laplace transform of f, is defined as the integral from 0 to infinity e to the minus st f of t dt. And notice this is a function of s. It's not a function of t because I get rid of t. And the caveat is this exists if f of t grows, well, why don't we write it this way? If the limit as t goes to infinity of e to the minus st f of t exists, and the integral above is finite. So the integral has to be finite, and f can't grow faster than the exponential kills it. Obviously, if I want the integral to exist, the integrand has to go to 0, but it has to go to 0 sufficiently fast, because as you know, dx over x just doesn't go, 1 over x doesn't go to 0 fast enough, because the integral dx over x is the log, and the log goes to infinity. So this is necessary but not sufficient for this. So really this is the condition, but this is a necessary condition. This is sufficient. You're familiar with what necessary and sufficient means. Go ahead.
Is that absolute value on the f of t?
Yes. And I have not told you why, but there's some mathematics here that I probably don't want to go into. I could prove the theorems here, but I think you'll hate me if I do
It's not
that.
necessary.
Okay. And let's just notice, yeah, so let's notice, what do I want to notice? Yeah, let's notice that S can be complex. S doesn't have to be real. In other words, you can have S is equal to x plus iy, where this is the complex plane, where I, if you like, is the square root of minus 1. In other words, I squared is equal to minus 1. So if I write this as the real axis and this is the imaginary axis, if this is x is the real part and y is the imaginary part, then I can think of this s as the vector x plus iy. And notice, this is in Cartesian coordinates. I can also write it as r e to the I theta. Actually, I have to be careful there. R cosine theta plus I sine theta. How do I know that? Well, if this is theta, then x is s cosine theta. So the x component is r cosine theta. And the y component is s sine theta. Just simple geometry. So x plus iy, r cosine theta is x, r sine theta is y. And I can define this as, by definition, as e to the I theta. So this is r e to the I theta. Now, you might say, why are you doing that? Well, up until now, you've probably only seen exponentials of real function, real things, not imaginary. If you want to extend exponentials from real to imaginary, You could say, how do I do that? Well, it turns out this is the only way that makes sense. You can prove, I'm not going to prove this, but you can prove if you want the exponentials to have the right form, the right values. E to the 0 is 1, e to the s1 times e to the s2 is e to the s1 plus s2. And e to any finite number is finite. The only possibility is this. And you can prove, so for homework, you should prove that e to the I theta 1 times e to the I theta 2 is equal to e to the I theta 1 plus theta 2. So show this. From just high school geometry, high school trigonometry, show that. Okay, so that's one thing to notice. The next thing to notice is the Laplace transform is linear. So the Laplace transform of f1 plus f2 is equal to the Laplace transform of f1 plus the Laplace transform of f2. And the Laplace transform of a times f is equal to a times the Laplace transform of f. And that's straightforward to prove because the Laplace transform is just an integral. And the integral of f1 plus f2 is the integral of f1 plus the integral of f2. Similarly, if I had a constant here, I can just pull it out of the integral. That's this. So this says that the Laplace transform is linear. What else can we see? Yes?
What does it say at the end of the homework?
Show. So it's linear. And what makes the Laplace transform useful, and again, I'm not going to show this, it can be shown that if f is single valued, then I can invert. I.e., if I know L of f, I can find f.
Did you write ICEST?
It can be shown that.
Okay.
That's the thing I never liked, but I mean, I'm happy to show it. But I would show that if you're interested in knowing where this stuff comes from, there's a course called Complex Variables, which is calculus with complex numbers instead of real numbers. It turns out the universe we live in, the natural set of numbers are complex numbers, not real numbers. So it makes much more sense to do calculus in complex numbers than real numbers. And it's kind of cool because things don't generalize the way you would expect. They do generalize. There's a math course for undergraduates called Complex Variables in the math department. And when there's demand, I teach a graduate course here called Complex Variables. Now, let me just, before I wrap up, let me just tell you what the inverse is. And the inverse, and I'm going to call this f tilde of s. That's going to be the notation I use for Laplace transform. And the inverse, f of t, is equal to the integral of e to the st f tilde of s ds. Well, that part looks easy. But then here I have gamma minus I omega, gamma plus I omega, and I have the limit as omega goes to infinity. So, what's going on there? And I have to tell you how to choose gamma. Okay, we're never going to do it this way, but this is the mathematical way. This says, remember I told you S can be complex. So S, yes, S can be complex, and if I wanted to actually, if I need to calculate the inverse, then the way I do it is I look at the complex plane, real, imaginary, and I look at all the points in the complex plane where, well, this is never goes to infinity for finite t, for finite s. But f can have certain points where f is infinite. So I look at all those points where f is infinite. And in fact, I can even have a line where f is infinite. Those are the singularities. The points in space, in the complex plane. You don't have to, this is for your knowledge, I'm not going to test you on this. There could be points, and there could even be lines, where the function f tilde is infinite, where it blows up. So what you want to do is choose gamma to the left of them. This is minus gamma right here, or gamma. Why don't we call it minus gamma? That doesn't really matter. This is the value of gamma. Gamma could be negative here. It's to the left of all singularities, and I've integrated on this line from minus infinity to plus infinity.
What's your y-axis here?
The imaginary.
Imaginary.
So remember, it's x plus iy. It's the thing multiplying I. Now, are you ever going to do that? First, you have to take complex variables to even know what I'm talking about. To know what a singularity is, to know what that integral is. That's not how we're going to do it. What we have is people have done a lot of that work for us. And there are these tables. And one of them is in your textbook. And I'll photocopy one. But there are tables. And the tables have f on this side of t and f tilde of s here. And the way we're going to do it in this class is we're going to look in the table for f tilde of s and then read across for f of t. That's the way we're going to do it. And there you find tables online. Because it's a lot of work to do it this way. And once someone's done the work, there's no reason to repeat it. Are there any questions? Gamma to the left of all singularities of f tilde of s. So, what are we going to do? What are we going to do in this course on this? The hour's over. What we're going to do with Laplace transforms is we're going to take our problems, we're going to Laplace transform them, solve for f tilde of s, and then try to go backwards. And what's the advantage of doing that? It seems like extra work. It seems if I want to go from here to 125th Street going via Queens. That doesn't sound like a good idea. I transform to Queens, go south, and then I come back. As we'll see at the beginning of the next hour, when I take the Laplace transform of a derivative or an integral, it gives me something algebraic. All the derivatives and all the integrals disappear. So I take a differential equation and I turn it into an algebraic equation. And that's worth going to Queens for, even if it is Queens. Any questions? So those are the coming attractions. Okay, so Monday is not a holiday, right? It's the week for Monday is a holiday. So I'm going to assign a homework. And remember, the material for the first exam ends before Laplace transforms. That's the material for the second exam. Any questions?
Laplace transform in chapter 4, right?
I think so.
All of chapter 3 is on the test?
Yes, everything from t equals 0 to the end of chapter 3. And let's see, where is the Laplace transform table? There's a certain page in the book.